So, no questions? We ready to go? Ah, we're already on, I see. Yes?
When we simulate, do we need considering the first arrive when the server in the vacation or just start server?
It doesn't matter. You're going to run it for hundreds of thousands of customers, so the initial condition shouldn't make any difference.
Okay.
Anything else? Okay, so what I want to do is finish up the stuff on polling models, and then that'll be it. All right, so I think we were sort of getting bogged down in details for a while, so I'm going to try and avoid that and get back to the big picture. So where we were was we were looking at a polling model, and we were trying to make the connection between the polling model and the vacation model. And the way we did that was to say, well, let's say here's a polling model. And if we look at this particular queue, let's call this QI, then when the server is serving all the other guys, from the viewpoint of that queue, you're on vacation. Now, what we've done is we've managed to get an expression, functional equation, for the generating function of the number of customers present in each of the queues at the instant at which I leave any particular queue. So in order to get this into the polling model structure, what I have to do is I have to look at all of the customers that arrive at a particular queue and recognize that some of those have a distribution just as if it was a polling model in which the other guys weren't there. And some of them have a distribution, see things, just as if they're in a vacation model. And others see things just as if they were in this queue by itself. So imagine that the system is completely empty. And then a customer arrives to QI, because we're only talking about QI. So that customer is said to initiate a supercycle. So when he arrives, the server immediately jumps to the queue and starts to serve him. And it serves him and all of his descendants. So there's a busy period. And at the end of that busy period, then the server leaves this queue and switches to the next one. So all of the customers who arrived and who were served during this busy period, to them, this is just an ordinary MG1 queue, because the existence of all of the other stations had no effect, since the first guy gets served immediately by the server just as an ordinary MG1, and then all of the descendants get served by the same, at the same place, regardless of the existence of everybody else. So while these guys are getting served, there are other people queuing up at these servers, or at these stations, I should say, but they have no effect on that. So let's call the fraction of customers that are served in this category in type 1. So there's going to be a probability for QI. Let's see, I want to use the same notation I used in the paper. Yeah, probability for QI for customers in class 1. And then there's going to be all of the other customers who are served at QI. That is, all the guys who arrive after the first busy period and before the system again becomes completely empty, in which case the whole process repeats itself. So let's call those other customers type 2. And that has to add up to 1. So all I got to do is find one of these, so I'll find that one. And then the argument goes something like this. You say, okay, here's where I'm going to calculate the probability that an arrival at QI is in class 1. And class 1, remember, are all the customers for whose waiting times are described by the ordinary Polacek-Kinchin formula for MG1. And then everybody else is described by the results for the vacation model, which you derived in your homework problem. Okay, so first of all, during a long period of time, the number of customers that arrive to QI is lambda I t. That is, t is a long period of time. So what I'm going to do is I'm going to divide the average number of customers that are in class 1 divided by the average number of customers total that arrive during a long period of time. Then I'm going to let the time get arbitrarily big and then cancel it out. Okay, now, if I look at a long period of time, the fraction of customers that arrive to QI is this. Lambda I is the number of customers Okay, so lambda sub I times t, or let's say lambda sub I times t is the average number of customers that arrive during the time t to QI. And of those, a certain number, 1 minus rho, arrive when the server is idle. Okay, so this is the number that arrive when the server is idle, so it's the number that initiate a busy period, initiate a supercycle. Now, we want to multiply that by the average number of customers that are served during a busy period, and that will give us the average number of customers that are served in time t that are either the ones that initiate the busy period, first busy period, or are served during that first busy period. And we've derived elsewhere in the course that the average number served during a busy period is 1 over 1 minus rho sub I. Okay, the rho sub I, the reason there's an I on there is that we're talking about a busy period defined by the arrival rate lambda sub I and the service times for QI. Now all you do is cancel out this guy right here, and what you're left with is 1 minus rho over 1 minus rho I. Okay, so the fraction of customers in category 2 is 1 minus that, so now we know those fractions. Okay, now we want to put this together. We want to say, what is the average waiting time for a customer in QI? And you say, well, there's two cases. First of all, let's look at all the customers who are in category 1. For them, it's just an ordinary MG1Q. So therefore, I'm going to multiply this fraction by the average waiting time for customers in an ordinary MG1Q with the parameters that correspond to QI. Well, that's given by lambda I, eta I double prime of 0 divided by 2 times 1 minus rho sub I. That's the Pollaczek-Kinchin formula for Q sub I, where the eta is the Laplace-Dirichlet transform of the distribution function of service times for QI. Okay, now what about the customers who are in category 2? For them, their waiting time is given by the result for the vacation model. And the vacation model, remember, had an average waiting time that was the sum of 2 terms by decomposition. One was what the Pollaczek-Kinchin result would give you for the case in which there are no vacations, and that's exactly this term right here. So the first term then is lambda sub I, eta sub I, double prime of 0 divided by 2 times 1 minus rho sub I. Exactly the same as here. And then there's the second term, and that second term has to do with the vacations, and that's defined by the generating function of the number of customers waiting at the station when the server returns from vacation. And so if psi is that generating function, or let's say psi I for QI, because it depends on the characteristics of the vacation for the particular Q, then the result was the second derivative evaluated at 1 divided by 2 lambda I times the first derivative evaluated at 1. Okay, so this is the decomposition result for vacation models, and this is the important part right here. Now when you combine these, since that plus that adds up to 1, then the result is that when I separate, I'm going to get one term, which is going to be just the Pollaczek-Kinchin formula, And then I'm going to get another term, which is going to be this probability times this thing right here. So how do I get this thing right here? And the answer is, well, the psi's are in fact the g's properly interpreted and evaluated. Okay, because remember that the psi is equal to the PGF of the number waiting at the end of a vacation. Now what we calculated was we calculated this generating function gi of x1 xn. And what this is was the generating function of the joint probability that at a switch point I'm leaving qi, and the number in the next q is given by the variable that corresponds to x1, and the number in the queue after that, x2, and so forth. So if I now differentiate these things and set all the x's equal to 1, then I'm going to get equations that I differentiate through implicitly. I'm going to get equations for the psi's, the second derivative and the first derivative, which I can then solve in terms of, I can solve because I have a sufficient number of equations, and the end results are these. Okay, so this is what happens when you do it. First of all, what you get is W, okay, now I'm looking at equation number 29 in the paper, in the second paper. Wi bar, so I'm going right from here. That's going to be equal to lambda I, eta I, double prime of 0 over 2 times 1 minus rho sub I. That's gotten by adding up that term and that term, plus psi I double prime of 1 divided by psi I prime of 1 times rho minus rho sub I over 2 lambda I times 1 minus rho sub I. So all this does is the arithmetic that was indicated right here. Okay? But this is what I want to get. All right, now, it turns out, according to equation 32, that this ratio, psi I double prime of 1 divided by psi I prime of 1, that turns out to be the following. I'll define what these things are in a minute. P0, which is the probability that, that at a switch point the system is completely empty, divided by lambda times 1 minus rho times m bar I minus 1 of 1 comma 1 divided by m bar sub I minus 1 of 1. Now, these m bars were defined as the, this is the a second derivative, this is a first derivative, or this is a partial with respect to one and then the other, and this is a partial derivative in which you then set the x is equal to 1. So in effect, what you're doing here is you're calculating these expected values. And when you do this and you plug this in, it turns out that the P0 cancels out. In the previous paper, the following is shown. It turns out that the m bar I minus 1 of 1, okay, which by definition, let me write the definition of that. That's equal to, well, here's the general definition. M bar I of k. So this corresponds to the kth position. This corresponds to the first position. Okay, this is equal to the partial with respect to the kth variable of this generating function evaluated at all the x's equals 1. So if you go back to the definition of the generating function, you see that this is essentially a mean value. When you differentiate implicitly through the functional equation that defines the generating functions, how they relate to themselves, you get a set of equations for these m bars. And if you solve those equations, what you get is that this is equal to, that's this piece right here, is equal to lambda I over lambda P0 rho minus rho I over 1 minus rho. Okay, that's very remarkable. But now, when you plug this into here and then do the equivalent for this thing now would be a partial of, with respect to xk, xj, for example, and do the same thing, then you're going to get some cancellation. And the end result is that the P0 cancels out, so that's going to cancel. And the answer then is found simply by numerically solving these equations. And that's it. That's all you got to do is solve them numerically. Now that may be a big job because the number of equations could be large, although it turns out that they're sparse. And it turns out that there are now, after all these years, many different ways of doing this. People have written this in different ways. And there are algorithms available for making these calculations. So that means that from our point of view, we can consider the problem solved, because the answer is given by this piece, which is just ordinary Polychek-Kinchin formula, this piece, which is essentially nothing, and this piece, which is obtained by solving a finite set of linear equations. If you could get them in closed form, that would be nice, but in general you can't. But nevertheless, you can take those equations and solve them numerically. So for all practical purposes, this problem is solved. Okay, now, the next step is to ask, well, look, what we have here is we have the solution for the case in which we have zero switchover times. But suppose we don't have zero switchover times, then what happens? Now, if you think about the model, go back here to the original model, you see that the zero switchover time case and the non-zero switchover time case, the relationship to them is problematical, because in the case of, let's look at the case in which we have non-zero switchover times. Imagine that the server takes a certain length of time to travel from there to there, and then when it finishes here, it takes a certain length of time to travel from here to here. In a general model, you want that to be a random variable. So you want each queue to have its own individual switchover time with its own individual distribution. Now, imagine that the switchover times go to 0. So as the switchover times go to 0, the server moves faster and faster. In the limit, as the switchover times approach 0, that means that the server is actually moving instantaneously from one queue to the next. If that happens, then whenever the system becomes completely empty, then the server is going to make an infinite number of cycles in a finite length of time. Now, that shouldn't have any effect on what the actual waiting times are, because nobody is waiting during the times that the server is making that trip. But nevertheless, in terms of getting one model from the other, the zero switchover time model doesn't follow from that, because in the zero switchover time model, the way in which you were able to solve it was by imagining that when the system becomes completely idle, the server stops moving. And then when someone arrives to one of the queues, the server jumps immediately to that queue in 0 time. So one model doesn't seem to be the limit of the other model, even though it does seem to be true that the waiting time in one model should be the limit of the waiting time in the other model. So everybody knows that if you look at the model in which the switchover times are not 0, that if you take limits appropriately, somehow or other you should get the answer that corresponds to the 0 case. But that seemed to be difficult, and the end result was that the subject kind of followed two paths. Some people analyzed and studied models with 0 switchover times separately, and other people studied models with non-zero times separately. And although they always claimed that you could get the 0 switchover time from the non-zero switchover time, very few said actually how to do it. And it was possible that if you looked at the non-zero model, which was more complicated, and then tried to solve these equations, the equivalent of these equations, for the case in which the parameter goes to 0 that corresponds to the time to switch from queue to queue, that the equations might fall apart. There might be indeterminacies there. So the point was that the subject proceeded in two separate paths. Now, recently, in a paper that appeared in Operations Research, we sort of solved this problem. Here's the journal. It appeared in the July-August 96 issue of OR, and I have some reprints, and I'll pass them out afterwards. Let me write down exactly, so I get it on the tape here, what the journal is. It's available in the library. The paper is by myself, Shun-Chen Nu, N-I-U, and Srini Srinivasan, S-R-I-N-I-V-A-S-A-N. And we've been working together on these polling and vacation models. We have an NSF grant, runs another couple of years. The paper that we published is called A Decomposition Theorem for polling models. And then it says the switchover times are effectively additive. The journal it appeared in is Operations Research. And this is volume 44, number 4, and that's July, August 1996. And the pages that appeared are 629 through 633. So let me state what the theorem is, the main theorem. Now, the paper, of course, is more complicated than what I'm going to write down, because you always make things more difficult than necessary when you write a paper. But here is the essence of the basic result. Now, I'm only going to look at the case of exhaustive service, but we did it for gated service as well. Here's the theorem. For exhaustive service, the expected waiting time at QI, for a customer at QI, is equal to the following. It's equal to the expected waiting time in the model with a 0. Let me write this down first, and then I'll explain what the symbols mean. R over 2, 1 minus rho sub I over 1 minus rho. Okay, what this thing says is we want to look at the expected waiting time in the model in which the switchover times are not necessarily 0. So this is what it is. This is the expected waiting time in a corresponding model in which the waiting times are 0. In other words, this is the model that we've just discussed. And this is a simple term in which R is the sum, or R is actually the expected value of the total switchover time per cycle. And the rows are as before. Rho sub I is the utilization of the ith queue, and rho is the sum of the utilizations of all the queues. Okay, so the R value is the average time it takes per cycle spent switching. Now, when R is equal to 0, then of course the expected waiting time in one model becomes exactly the expected waiting time in the 0 switchover time model. So that's exactly what you would expect. The interesting thing here is that if you look at the model, Here are the queues. When the server switches from one queue to the next, then customers are arriving, and they're arriving at all of the queues. And so the more time I spend switching, the more time I spend serving. And the more time I spend serving, the more queues, the more customers there are waiting. And then when I switch again, and during the switchover time, which is dead time in a sense, the server is removed from serving, from working, it's just moving, then the same thing is going to happen. And these times are interspersed with the times actually spent waiting. So it's surprising that the effect of the switchover times should separate. In fact, this is just like a vacation model, except that the reasons for it are not the same. The proof is different, the format is different, but the end result is similar in that for the case in which these dead times, they're sort of like vacation times. In the case in which those dead times are not zero, what you get is a separation between the effect of what happens during the switching, which has nothing to do with the queuing process, and what happens with the queuing, which has nothing to do with the switching process. So even though during the switching time, customers are arriving and they're causing the queues to grow larger, their effect is separated in this term and is not in this term. What that means is that if I can solve this model, which we can, then if I want to solve the model in which the switchover times are not zero, instead of solving that more complicated model, I just have to add on this piece. So that's a major simplification from a practical point of view. It's also a major theoretical insight. Now, I'm not finished with the statement of the theorem. Okay, so the W0, this term here, is for the so-called corresponding model. Now, what do we mean by the corresponding model? Well, the corresponding model is a model that has exactly the same parameters as the original, except that the switchover times are zero, and one other exception. The second moment of the service times in QI, written that way, is given by the following. Another second moment, I'll explain this in a minute, plus delta squared sub I minus 1 times lambda I r divided by 1 minus rho to the minus 1. Now what this is, this says that suppose we look at this model right here, which is the one in which the switchover times are not necessarily zero. And in that model, QI has arrival rate lambda I. Okay, so here's QI. It has arrival rate lambda I, and in the notation of this, which has been adopted in recent years, the service time has a distribution whose mean is B sub I, and whose second moment is BI super 2. In other words, this defines the mean and the variance of the service time. So what this says is that when I want to get the corresponding model, what I do is I simply solve exactly the same equations, except that instead of using the original second moment, the original variance for the service times, I use a new variance, which is the original one plus a term. Now this term, the delta squares, correspond to the variances of the switchover times. Okay, so delta I minus 1 squared is the variance of the switchover time from QI minus 1 to QI. If the switchover times are constant, then the variance terms are zero, and the corresponding model is the true model with zero switchover times, because this term goes away. But if the variances of the switchover times are not zero, then in effect, the variability of the switchover times is combined with the variability of the service times. And so the new model has the same structure, but it has a greater variability of service times. And then you get this piece that separates out. Now, if you look at this piece right here, this term, the reason it's written as the reciprocal is because this term itself has a interpretation. And that term is equal to the mean number of customers served at QI per cycle. Remember that R is the average time it takes, it's spent in traveling around the system, and rho is the utilization total of the server. So this term is the average number of customers that are served at QI per cycle. And what this does is it says, okay, I'm going to apportion the variance effect of the switchover times by multiplying the number of customers served by an additional variance term that corresponds to the time it takes me to travel from QI minus 1 to QI, and combine those. So in effect, what happens then is that this formula says that the effect of the variability in the service times can be removed, and imagine that it's actually included in the variability of the service times simply by replacing the old service time by the same thing plus this extra amount. And that if you do that, that what you get then is the waiting time is the sum of the waiting time in the corresponding model, which has the new increased variability in service times, but exactly the same mathematical structure, plus a term that you can compute in your head that requires no calculation. So the conclusion of the theorem is two things. One is that if I have a algorithm or a computer program that computes these values for the zero switchover time model, then for the non-zero switchover time model, I need only add on this piece. The second thing is that it shows some interesting things. For example, it shows that the average waiting time at QI does not depend on the switchover times as far as this term is concerned. It doesn't depend on the switchover times at QI. It just depends on the sum of the switchover times. So I could take these switchover times and I could apportion them, the constant portion, and I could apportion them any way I want in the cycle, and the effect would be exactly the same. And I could see exactly what would happen. For example, if someone said, okay, what I'm going to do is for some reason, I'm going to simply make the server sit idle here for a certain length of time, what would the effect of that be? The answer is, well, all you would do would be to add that length of time into this R, and that would be the effect. Now, the effect, of course, depends on the utilization, so it's magnified by the utilization, but it doesn't depend on all of the other things that appear to be interacting. There doesn't seem to be any reason for this that I could think of. It's just that it works. The original case, the case in which the delta squared were all zero, which is the case where the switchover times are constant, that was originally solved by Furman. Furman was my co-author in the paper on vacation models, the 1985 paper by Furman and Cooper that generalized the results from the 1970 vacation model. And so Furman and I and some other people have been thinking about these things for about 25 years now. And so we've sort of got a lot of this stuff, I guess it's in our genes by now, and so we think about these things in a certain way. At exactly the same time Furman was working on this question I was, but Furman beat me to it. However, lucky for me, Furman only considered the case in which the switchover times are constant, so he didn't have this term right here. Now, his method was completely different from the way I looked at it, and that's the reason that he didn't come up with this piece. It turns out that this piece is really very important, and I'll give you a reason for that in a moment, an example of that fact in a moment. Okay, so the main thing here is that now we have a connection which shows that, in fact, the zero switchover time model is really the basic model. It's really more basic. It's not really appropriate to take the non-zero case and look at the zero case as a special case. It's really better to think of this as the general case, and that the other case is simply that plus a term. The proof for this is really simple and algebraic. All you had to do was realize that this is the way to go, that that this was a true statement. And the proof is by taking the equations written by Ferguson and Amanetza for the non-zero switchover time case, and recognizing that those equations could be manipulated in such a way that they would be factored, and they would factor into two pieces. And one piece was exactly what you got without the switchover times, and the other piece had all the switchover times. So it's just a matter of arithmetic once you see what to do. This is outlined in the OR paper. Okay, any questions about this? We also did this, by the way, for the gated model. And in that case, the results are essentially the same. Basically, all is a change right here in this term, as it's delta squared sub I instead of I minus 1. And there's a change here. I think this is a plus instead of a minus. Doesn't matter. All right, now let me tell you a way in which this result here was actually used that was very interesting. In manufacturing engineering, as opposed to telecommunications, people are interested in these same kind of models. But there, instead of talking about switchover time, they're interested in what they call setup time. The idea in the manufacturing context is that there's work waiting to be done at these various stations, and some machine goes over and does this work. And when the machine does the work, it spends a relatively large amount of time working and a small amount of time in being moved from one place to the next. So the switchover time is tiny compared to the time spent working, so therefore people don't worry about how much time it takes to move. But when it gets there, the machine has to set up. That is, you can't use the machine in the same settings here and here. So once you move the machine, then you have to do some work to it. In fact, it really doesn't matter from a mathematical point of view whether you call the times setup times or switchover times. It's still an amount of time that the server is withdrawn from its ability to work and is out of commission until it then starts to work again. So it really doesn't matter mathematically what I do it, how I call it. But in the context of manufacturing, people talk about setup times. Now, one of the assumptions about manufacturing theory is that if you have machines that do work and time is wasted by having to take the machines and set up, that you can improve things by minimizing your setup time. So everybody's viewpoint was that all things being equal, once you have a solution, if you took the same solution and somehow or other could make the setup time smaller, then the average waiting time would be less, would decrease. So everybody believed this, and then a few years ago, Sarkar and Zangwill, two researchers working in the area of manufacturing systems, calculated some numerical examples, and they showed by numerical example that they could construct cases where if they reduced the setup time, the waiting times would actually increase instead of decrease. So this didn't make any sense. And then they published articles in which they said that this is a very important and fundamental result, and it raised the hackles of a lot of people in the manufacturing community, because it was just common sense that it must be true that if you decrease the setup times, you're saving work. I mean, it doesn't make any sense to think that if I get to work faster, all the while customers and work is arriving, that somehow or other that's going to make things worse. Well, people criticize their result on the grounds that they said, well, we can't find a mathematical mistake, but it's not a good model. In particular, what Sarkar and Zangwill did was they took cases where the variances were ridiculously large. And so people said, well, this is just some kind of mathematical anomaly, but it has nothing to do with real life. And Sarkar and Zangwill said, well, you really don't know that because you don't understand this. What we did is we showed that the phenomenon exists, and now unless you could show that it's not important, you should think about it. You should worry about it because maybe it is important. So that means that the question is open of how do you explain the fact that cutting setup times could actually increase waiting times. And now Srinivasan, Nu, and I started looking at this question again because we felt that somehow or other it was related to this theorem. Because in this theorem, what this says is that the setup times or the switchover times, in effect, separate out. So we ought to be able to analyze the problem because we've broken this down into a thing where there are no setup times and then the effect of the setup times. So our attack, our strategy was to use exactly the problem that I've given you. In fact, that's why I gave it to you in the renewal theory case. That is, let me write down what we did. All right, first of all, we're going to look at the symmetric model. Okay, so let me go back to here. I'm going to look at what's called the symmetric model. The reason is that what symmetric means is that all of these Q's are the same. They all have the same lambdas and the same B's, and the switchover times or setup times are all the same. Now, in fact, if I had to look at one single model, that's probably the best one. If the effect is in here, then it's not because of bizarre imbalances in the Q's. So look at the symmetric model. Now, if you look at the symmetric model, then it turns out that you can actually evaluate this part. Because in the symmetric model, if there are no switchover times, then every Q is exactly the same, which means that when I switch from one Q to the next, if I do it in 0 time, it doesn't have to be considered to be a separate Q. In fact, in the case of 0 switchover times, if all of the Q's have exactly the same parameters, then this is equivalent to looking at ordinary MG1, in which I'm simply using a strange Q discipline. But the Q discipline does not affect the average waiting time. So that means that in the case of the symmetric model, the expected waiting time for the ith Q is the same for all I, and this part can be written down explicitly. And in fact, it's the Pollaczek-Khinchin formula. So that means we need only worry about this part. Okay, so now, instead of taking the viewpoint that we are going to cut the setup times or the switchover time, now I'm going to take the viewpoint that the, well, here's what I'm going to say. I'm going to let the switchover time at each Q be called Z sub delta. So this is the switchover time at each Q. It's the same for every Q. It's the same as the setup time now at each Q. And that's going to be the sum of two pieces, Z plus delta. Now, Z is random. It's a random variable. And delta is a constant. Now, if that's the case, then the expected value of the switchover time is equal to the expected value of Z plus delta. The variance of the switchover time is equal to the variance of Z, because the variance associated with this piece is 0. So the trick is that I can now assume that I have a symmetric model in which the corresponding model is just MG1, and the MG1 corresponds to the model in which the service times have been changed this way, and I'm going to pick the setup times or the switchover times to be this, so that when I get my answer, which I can now write explicitly, I can then vary this delta. As I vary the delta, this piece isn't going to change because it doesn't affect the variance. And so the only piece that's going to change is the other piece, and I'm going to get a formula in which I can see how everything depends on delta. Now, instead of imagining there's a fixed delta which I'm going to cut, or I'm going to cut some switchover time, what I'm going to do is I'm going to show that if I let the delta vary from 0 on up, that under certain conditions, as the delta goes up, the expected waiting time goes down. So in other words, what it says is that if I had a system in which the setup times were given by this random value right here, whatever it is, then under certain conditions, I could decrease the average waiting time by adding in a value of delta, that is, putting in a constant idle time, which can be put in any place in the cycle or distributed throughout the cycle. That is, I simply force the server to be idle for a length of time delta, and by doing that, I actually make the waiting time decrease. Okay, let me write out what the answer is. What I'm going to do is I'm going to rewrite this formula now for the special case in which the Q is symmetric. That is, now all of these Q's are the same. And the answer turns out to be this. It's rho over 1 minus rho, B2, second moment, divided by 2B, plus 1/2 times the variance of the setup times, or switchover times, divided by the mean of the switchover times, plus that same term, the mean, times n minus rho over 1 minus rho. Now, if you look at this piece right here is the ordinary Pollaczek-Khinchin formula. And that comes out of this term. Because what I do is, well, first I write the Pollaczek-Khinchin formula, because remember, in the zero switchover time model, if it's symmetric, it's just like MG1, except that instead of having a service time second moment given by this, it's given by the sum. But when I plug into the Pollaczek-Khinchin formula, which is this, but I replace the B by this, what I get is two terms, one of which is the same as the one I already had, and the other of which has this in it. Okay, now this is the variance, and this is going to specialize for the case in which we have all of the switchover times having the same distribution. In particular, if I now take this second piece plus that piece, for the particular case in which the switchover or setup times are the same for each Q and consist of a random part plus a constant part, then this is what I get. Okay, so this is ordinary MG1, and this is the effect of the setup times, including in two separate pieces, the variable part of the setup times and the constant part of the setup times. Okay, now what you see here is that if I keep this constant and vary that, then I have two terms. In this term, the variance remains constant, but the expected value in the denominator grows. So as the delta grows, as I let delta range from 0 on up, this term is going to get smaller, but this term is going to get larger. And the question is which one dominates, and that depends on the particular numbers. But you can choose numbers for which the expected value of the waiting time looks like this. And this is exactly the kind of result that you found in your renewal theory homework. And in fact, it's exactly the same result that's going to appear in the take-home exam in the final. Okay, what happens is that when delta is 0, there's a waiting time which would be given by mg1 plus some constant here. So this is the case in which you have variable switchover times, but the constant term is 0. And then, as you let the constant term grow, what's going to happen is there are two possibilities. One is that this term dominates always, and you get that, which is the common sense view. And the other is the case in which there's actually a minimum here, because at first, this term dominates. And so what happens then is it would look like this, and as the delta gets bigger, this part gets smaller, that part gets bigger, but the sum gets smaller, and then it goes like that. So this shows that if by forcing the server to be idle, I can actually make the waiting time decrease, then it's clear that if I already have a certain setup time. If I force it to be smaller, if I cut it, then I could make it increase because I'm simply moving the curve back that way. So that explains this anomaly. Let me give a numerical example. We have a paper in which the stuff that I'm going through now is presented. The paper is under review, so I don't know what's going to happen. I assume it'll be accepted, eventually, but these papers always come back with comments that you have to argue about. Okay, here is the specific example we chose. Suppose that n is equal to 4 q's. They're symmetric. We're going to assume that we have constant service times. So we're going to assume that B and its second moment are both 1. So we're assuming constant service times with service time of 1. Now that's interesting because remember that the service times come into play only in this term. It wasn't clear at the beginning because people said, well, you chose exponential service times, you chose this service time. The assumption was that the anomaly might have been related to the particular distribution of service times. But this part is a constant with respect to the switchover time, so it doesn't make any difference what it is, so we're just picking the simplest case, which is the case of constant service times. Okay, so constant service times. Then we took the case, we had to pick a value of lambda, so we took it so that rho is equal to 80%. So 80% utilization seems like a reasonable number. Okay, then we took the switchover times as given by this, where the expected value of z, okay, the expected part of the variable part of the switchover time is equal to 1/4, and we took the variance to be equal to 4. So the switchover times are highly variable, 16 to 1, but nevertheless not ridiculous. Okay, so what does that mean? That means that delta star, which I hadn't defined, but I'll define in a moment, delta star is the value of delta that makes this a minimum. So what you do is you differentiate this with respect to delta, you set it equal to 0, and you call the value of delta that produces the minimum delta star. So if there is a minimum, actually there's a formula, and the formula is that this delta star is the maximum of 0 and something else. And if there is no minimum, then the something else is negative. And if there is a minimum, then it's bigger, and then that means that the curve goes down. Okay, so the delta star in this case will turn out to be 1/4. So then delta star is equal to 1/4. Okay, so that means that for our example, that's it right there. Okay, so what happens then in this case is that rho over 1 minus rho times the second moment of the service times divided by 2 times the mean, that turns out to be 2. So this is the amount of the waiting time in this formula that there would be if there were no setup times or no switch over times. This is just the ordinary Pawlicek-Kinchin formula for MD1. Okay, now what about the other part? Now we have this component, the thing in brackets. So first I'll do 1/2 of the variance plus the expected value plus 0. In other words, I'm going to take the particular case in which delta is equal to 0. So this is the case in which I have no inserted idle time. Delta is the amount of idle time I'm going to insert there artificially. So if I insert none, then this term becomes, so this would be E of z plus 0 times n of course is 4 in this case, minus rho divided by 1 minus rho. This turns out to be equal to 10 if you do the arithmetic. And finally, I'll write it here, if I take the same term But now I'm going to put in the value of delta star, which is plus a quarter. I'll just write it as delta star, plus the expected value of z plus delta star times n minus rho over 1 minus rho. That turns out to be equal to 8. So putting in delta star equals 1/4 makes this term right here equal to 8, but putting it in equal to 0 makes it equal to 10. Okay, so what that means is that if I look at the effect of the setup times, remember if there were no setup times, the average waiting time would be this. So if the average waiting time is this, that means that the effect of the setup times is as follows. 10 is what the answer would be, namely it would be 2 plus 8. Okay, so 10 minus 8 divided by 10, that means a change, a reduction of 20%. So if the setup times were given by this part alone, and this guy weren't there, then the effect of introducing a forced idle time of 1/4 of a unit for each queue, or since there are 4 queues, a total of 1 unit of forced idle time per cycle, this would save me 20%. Okay, that would be the effect of the setup times. Overall, the amount goes from 12 to 10. Divide that by 10, by 12, and that's about 16.7%. Okay, so let me clarify what these two statements say. This value right here, with the 0 in here, is 10. So if I had, if I looked at the effect of the setup times, which is this piece right here, and I had setup times, but I had no idle time, and then if I introduced the idle time, then this term would go from 10 to 8, or in other words, it would be a reduction of 20%. So by introducing a delta star, which is 1/4 per queue, or in other words, introducing 1 unit, or the equivalent of 1 service time per cycle, during which the server is forced to be idle even though work is waiting, then the effect of the setup times reduces from 10 to 8, or is a 20% decrease in the effect. Overall, the waiting time will have decreased from the 10 plus 2, here's the 2, which is in there originally, which I can do nothing about, or 12, to 8 plus 2, or 10, or a reduction in overall waiting time of 16.7%. Now in the paper what we did is we did this in general and just gave this example as a specific case at the end. But the general part is very complicated, and although it gives formulas, it really doesn't give much in the way of insight. All of the insight is right here, and you see that the result is caused by the fact that there are 2 terms, which is basically the renewal theory result. One is the ratio of variance to mean, and the other has the mean. That's exactly what happens in the renewal theory result when you interrupt an interval. You get a piece here that depends on the ratio of the variance to the mean. Okay, so as long as, if I can then increase the mean and keep the variance constant, which I can do by simply adding on a constant term, the result is that I can make this term get smaller and this term get larger, and with the proper choice of the numbers, this one will dominate at the beginning, and then this one will dominate, and you get exactly this behavior. Okay, so this example right here, drawn on this graph, this is the value, let's see, this would be the value 10. No, it'd be the value 12. Okay, that's the 12. So it would start out at 12, it would drop down to 10, and then it would increase. Okay, the conclusion then is that we proved the theorem that shows that in polling models, just like in vacation models, although for different reasons apparently because the same conditions are not met, that somehow or other the effect of the vacation or the effect of the switchover time, it's the idle time when the server is not available, even though it's confounded with the queues, the numerical effect can be separated into two terms, one of which has the queues, one of which has the idle times, and you can therefore look at the effects separately. Then we can apply that to this particular model, which is, in this case, is a polling model with symmetric polling model in which each queue is the same, and we just picked some numbers, and we showed that if we represent the switchover or setup time by two pieces, a random piece plus a constant piece, then we can manipulate the constant piece, and you can see it in the formula, in such a way that by increasing the constant piece, you decrease the average waiting time, which means that by forcing the server to remain idle by a fixed amount per cycle, even though it can be distributed any way you want throughout the cycle, and even though there is work waiting to be done, by forcing the server to be idle, you can actually decrease the total waiting time for all the queues. That's completely counterintuitive, and that's the kind of stuff that, to me, makes queuing theory interesting. The idea that there are results that any sane, ordinary person would say can't possibly happen. See, most mathematics, if it's surprising only to mathematicians. You can't go to a cocktail party and explain the problem to somebody in topology or something of that sort and have them say, wow, that's amazing, unless you happen to be a mathematician. But you could go to a cocktail party. Well, it would have to be one that was populated by nerds, but they wouldn't have to be mathematicians who would listen to you, and you would say, look, I have this server, and I have this work waiting, and I'm going to make the server sit idle even though there's work to be done, and believe it or not, that'll get the work done faster, and they'll say, no, you're crazy. Okay? And here you can prove it. Okay, are there any comments or questions or anything about where we stand? I guess where we stand is we're over. Did I pass this out? Or I didn't pass it out. I got them right here. Okay, so here is the reprint, but you can go to the library and read it in the journal. You share. There's also another paper by myself, Srinivasan and New, that generalizes this from average values to distributions. And we're working on extensions of this now. Another new surprising result. I don't have time to go into it here, but it is, it's very surprising, and it's also top secret. Because it's one of these things, I think, that if it gets out, somebody else will beat us to the punch. Because other people write faster than we do. Okay, so are there any questions about anything? The course, homework, exam, strategy, future work? I hope that some of you find this interesting and would like to do some future research. For example, if you want to do a dissertation, then of course that requires some advance in the theory somehow or other, although there are lots of things that can be manipulated. If you want to do a master's thesis, then it really requires just writing something that's sort of an overview and taking a piece of it and examining it. For example, you could take these results and you could write a simulation, and then you could compare the simulation with the theory, and you could see whether it works. Of course, it has to, or your simulation is wrong. But that's a reasonable master's thesis. And there are lots of versions of that that could be done. So if you're interested, let me know. Okay, so if there's nothing else, I've enjoyed the course. I hope you have. And maybe I'll see some of you again sometime. Okay, we're done. You can, all right, one last. Which, of course, you that would give you a utilization of 1. And for think time or infinity, the utilization would be 0. So you're going to get some kind of curve. There's some kind of curve that looks like that. Okay, so what you do is you pick a value